Welcome to another Advanced Topics lecture. This one is for valence shell electron pair repulsion, also known as VSEPR. Notice it is a theory. It has powerful explanatory power, but it is not the same thing as the reality. It's merely a particular way of looking at or making predictions of the shape that molecules will take given certain facts about their valence shells. You notice the word repulsion and the word electron. Electrons obviously repel each other, being like in charge. And actually it helps to answer a question which pops up quite a bit. Water, as a molecule, is H2O. We often just commit this shape to memory. This is also, this particular shape follows from VSEPR theory. But the question that readily pops up is, well, why can't water assume this particular orientation? Why is it bent and not linear as it would appear to be right here? Well, according to valence shell electron pair repulsion, there is an interaction between valence shell electrons. Now, there are two kinds of valence shells electrons. There are those that are involved in bonds. We call those bonding domains, or I call it a BD, a bonding domain. And there are those that are not. There are those that are just on the central atom or the other atoms, and they're not part of the actual formation of bonds. But even though they're not part of bonds, they seem to be almost spectators. They actually have an outsized influence on the shape of the molecule. The electrons in a bond tend to be pretty compact. They're less influential on the rest of the atom. But if you have a non-bonding domain, like here, they happen to have a very large effect. And obviously, two non-bonding domains are going to affect one another in such a way that they're going to force themselves away from each other. And not only that, the negativity here is going to repel the negativity here. So it's going to force this into the pattern that it currently holds. You can think of it this way. If I imagine that I have the electrons here, this set is putting downward pressure on this bond, and this set is putting downward pressure on this bond, causing the bonds to move away from one another. Of course, as that happens, as the bonds themselves get closer to one another, well, they repel each other. So it's kind of like a negotiation. The non-bonding domains are forcing the bonding domains down here, but the bonding domains then repel each other like so. And the resulting shape is a bent molecule, and a bent molecule with an exact angle. The angle between these two hydrogens in this bond is always going to be about 104.5 degrees, a consequence of this theory. The theory is very good. Of course, there are exceptions to the theory. That's why I said that theories are only have limited value depending on depending on the particular perspective that we take when we judge an object in nature. Well, let's also go back and talk about what it means to be a valence electron. Well, a valence electron, or I should say a valence shell, generally speaking, is satisfied, is stable, when it is occupied by 8 electrons. It's called the octet rule. The central atom in a molecule has 8 valence electrons. An obvious example, an exception would be hydrogen. Hydrogen has 1 valence electron, but it is happy when it has 2. Remember, it only has 1 shell, and as we know in the first shell, there can only be 2 electrons. That's going to be an exception. Hydrogen will be happy forming 1 bond, and not each. So please, don't do this. Don't try to give hydrogen 8. It simply can't handle that number of electrons in its first shell. With that said, there are very, very large atoms that, given their size and therefore their sheer number of electrons, they are able to form something called an expanded octet. meaning that they will not be satisfied with merely 8 electrons. They can have a total of 10 or 12 valence electrons, meaning they can form 4, 5, 6 bonds, and also other non-bonding domains, which I'm getting ahead of myself. I shouldn't say such things at this point. There are smaller atoms, and as a result of being small and having fewer electrons, they have a smaller potential to take on electrons. Therefore, they're going to be satisfied with 2, 4, or 6 valence electrons. Once you draw a shape, for example, I drew water a moment ago, and when I do a count, I see that I have 2 bonding domains, 1, 2, and I have 2 non-bonding domains. Now, the way that I've drawn it means that I can see that it's a bent shape, but I can refer to a table, and the table of shapes and as a function of bonding and non-bonding domains. In the case where I have 2 bonding domains and 2 non-bonding domains, it will assume what we call a bent shape, or also it's called angular. These are both synonyms, mean the same thing. But the question is, how do I draw the molecule in the first place? Again, once I draw the molecule, I can count up bonding domains and non-bonding domains, come to my table, and look up the shape. That is, unless in your class you have to memorize them, in advanced topics we do not have to. Let's take a molecule. This molecule is PF4, and it has an overall charge of -1. The first thing that we do towards drawing the molecule is we count up the total number of valence electrons that are supposed to be in the molecule. If there's a negative charge, we're going to add 1 electron. However, if there's a positive charge, we're going to subtract 1 electron. Phosphorus is 285. Fluorine is 27. So phosphorus has a total of 5 valence electrons. I have 4 fluorines. Each one has 7 valence electrons. Notice this has a -1 charge. That means when I formed the atom, I had to pick up an electron from outside, and I had to add it to the total number. So 5 plus 28 plus 1 is 32. I should say, I'm sorry, 34 electrons. So I know that once I reach 34 valence electrons in my molecule, I am done. Now it says draw single bonds between the central atom and the peripheral atoms. For molecules that have what we call expanded octets, they're essentially always going to have single bonds. So I draw the P in the middle, and I have fluorines going all around like this. Single bond, single bond, single bond, single bond. Now the fluorines follow the octet rule. They're happy with a total of 8 valence electrons. Remember, the bond itself counts as 2 electrons. 4, 6, 8, 2. 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now notice I have a total of 32 electrons, but at the first I counted up that I needed a total of 34. I'm supposed to have 34, I have 32. That means that there are 2 extra electrons that are unaccounted for. I have to add these electrons to the central atom. So if I resketch this, there we go. And as I said, this represents a total of 32 electrons. I have 2 more to place, so I'm going to place the remaining 2 on the central atom. Now it says count up the total number of pairs of non-bonding electrons. Remember that at the beginning, I said the non-bonding electrons were these pairs on the outside. They're not forming bonds. So if you notice, and I'm sorry, I should also say this, the non-bonding electrons are only counted on the central atom. I just have 1 pair of non-bonding electrons. I skipped this, 5. I'm supposed to count up the total number of bonds on the central atom. We'll take a look. I have a total of 1, 2, 3, 4. So I have 4 bonding domains. And as I said, I have this one sole pair of non-bonding electrons. So I'm going to go to my table and look up 4 bonding domains and 1 non-bonding domain. And I'm going to see what shape I see. And that shape is a seesaw shape. Now, if you're drawing, or I should say, it doesn't matter if your drawing resembles a seesaw. As long as you are able to see the number of bonding domains, which are 4, and the number of non-bonding domains, which is 1, then you've gotten all the information you need in order to be able to use the table. Now the question is why, if you're curious, why is this a seesaw shape? How is that a seesaw? Well, for one, if I imagine that the P is the center of the seesaw, and these F's are 2 seats, I have 3 other domains around this midsection. Imagine that they're coming up, they're 120 degrees from each other. And if we imagine that I put an F here and an F here, these are bonds. And this last part is not a bond, but a bonding domain. You actually can see that this looks like a little seesaw. That's why they call it seesaw. 2 little merrymakers on here. So this is why we can call it. That's why it's actually the accepted term. You also can call it a distorted tetrahedron. Distorted tetrahedron. Anyway, why don't we look at a sample problem on homework? This is question number 2. It's the I3 minus molecule. Remember, the first thing that we do is we have to count up valence electrons. Oh, we jumped over there. Count up the number of valence electrons. Well, if you notice, I have, 1 second, I have 3 iodines. Each iodine has 7 valence electrons. It's 2, 8, 18, 8, 7. It's the last number. And don't forget, there's that -1 here, so that means I have an additional electron. So I have 22 electrons to place. Now remember the rule. I'm going to place these around a central atom. They're all the same. They're I, and I. So I'm just going to make one of the I's a central atom. And I'm just going to put them anywhere. I'm just going to put them in a straight line. Maybe it's in a straight line, maybe not. It doesn't matter. And I'm going to put single bonds between them. Now, as I said, the side atoms, the peripheral atoms, are happy with 8. 2, 4, 6, 8. 2, 4, 6, 8. Now we do a count. Have I reached 22 electrons? Well, 2, 4, 6, 8, 10, 12, 14, 16. Ooh, I have 16 electrons. That means I'm 6 shy of where I need to be. Well, I'm going to put those 6 electrons, in other words, 3 pairs of electrons, on the central atom. So I'm going to put a pair here, a pair there, and a pair there. Now, I do my count. How many bonding domains do I have? Well, on the central atom, I have 2 bonds, 2 bonding domains. How many non-bonding domains do I have? Again, I only look at the central I. 2, 4, 6. I apologize. Domains. I have 3 pairs, there's 3 domains. When I go to my reference table, I see that 2 bonding domains and 3 non-bonding domains is simply a linear molecule. Again, there is a geometry here. For example, these are all 120 degrees from each other. These are 180 degrees or 90 degrees from the central atom, from these. But you're not responsible for the angles. The story gets more interesting when you go into the angles and the nitty-gritty of this. This is the extent of what you need to know to do this. So again, I found out, I drew my molecule, I counted up the number of bonding domains and non-bonding domains. I went to my chart, and I saw that it had to be a linear arrangement. Well, thanks so much. I hope you found this helpful. Of course, pop in to 0 period if you need more detailed instructions. Bye-bye.